In this video, we are going to talk about dynamic equilibrium. And you're going to kind of have to forget some of the stuff you learned about chemical reactions in order to understand some of the concepts in this video. Let's take a look at an analogy. So it's a hot, sunny day, and there are a bunch of people hanging out by the pool. And I'm going to write this out like a chemical reaction. So we have a group of sunbathers, and eventually they're going to turn into swimmers. So this is our reaction. We have sunbathers are our reactants and swimmers are our products. So normally you think of a reaction going like this. Well, all the sunbathers turn into swimmers and then the reaction is done. That's how we learned about chemical reactions, where a reaction starts and then it stops when all of the products are formed. Now, this is not how the real world works. We don't have chemical reactions that just start and then stop when all of the products are made. We don't have that taking place. What we have is something called equilibrium. And what we're going to do is I'm going to show you in a little bit of slow motion what really happens in most chemical reactions. Now, it doesn't happen to this extent, but it happens in most chemical reactions to some extent. So we start off with 12 sunbathers and 0 swimmers, and then we have 11 sunbathers and 1 swimmer at the beginning of the reaction, and then we have 10 sunbathers and 2 swimmers as the reaction proceeds. And then we get more and more swimmers as the reaction goes on, and then we end up with 9 sunbathers and 3 swimmers. But then something happens. One person gets into the pool and another gets out at the same time. We've never talked about reverse reactions taking place. Well, then we continue on and another person jumps into the pool. So now we have 8 sunbathers and 4 swimmers. And now we have 7 sunbathers and 5 swimmers, and now we have another swimmer. One more joins the swimming pool, and now we're down to 6 sunbathers and 6 swimmers. But then something else happens. One person goes in and another comes out, and one person goes in and another comes out, and then we have the forward of the reaction taking place and the reverse taking place. And what we're left with is a pattern of equal amounts of sunbathers as we move down and equal amounts of swimmers as we move down. But the reaction is still taking place. There's still movement happening. The reaction didn't stop. Now, that line where it starts to, everything below it remains equal, the quantities remain equal. That line represents the beginning of equilibrium. So the amount of reactants stays the same, but the amount of products stays the same. But this is called dynamic equilibrium. The reaction didn't just stop giving us 6 and 6. It kept going back and forth at equal rates. And when we represent this symbolically, we don't use an arrow anymore. We use a double-sided arrow. So an arrow going to the left and an arrow going to the right. And this is typically what you'll see in most textbooks, is that kind of half arrow, double half arrow. So here's a more formal definition of dynamic equilibrium. So dynamic equilibrium, it's reached when the concentrations or amounts of the products and reactants does not change. So we had 6, 6, 6, 6, 6. And then we had 6, 6, 6, 6, 6 all the way down, and it wasn't changing, but it's dynamic because the reaction didn't stop. It keeps going, but it keeps going back and forth at equal rates. Now let's take a look at this example. We have a molecule of hydrogen and a molecule of iodine combining to form 2 molecules of hydrogen iodide. Now at the beginning of this reaction, we have all reactants and no products. So we're starting off with lots of reactants, kind of like our sunbathers, and 0 products, kind of like our swimmers. So this is the beginning of a reaction that will eventually reach equilibrium. It takes a while sometimes for reactions to reach equilibrium, but we start off with a high amount of reactants or all reactants and no products. And as the reaction continues, the number of hydrogen and iodine molecules decreases and the number of products or the number of hydrogen iodide molecules increases. And as the reaction continues, we have more and more and more hydrogen and iodine turning into hydrogen iodide, but we also have the reverse taking place. We have a couple hydrogen iodide molecules going back and turning back into hydrogen and iodine. And the reaction continues to progress, and it continues to progress until it reaches equilibrium. Now, you'll see that we have this peak amount of products, so hydrogen iodide molecules, and we have this steady state, this low amount of reactants, which would be the hydrogen and the iodine molecules. And notice they don't have to be equal quantities. They were in my sunbathers and swimmers analogy, but they don't have to be equal. We have, in this scenario, we have way more products than reactants. You can see the amount of reactants is lower than the amount of products. And here we've reached equilibrium. So the amounts don't change. They don't necessarily have to be equal to each other, but they have to be unchanging. However, the reaction is still taking place. It's important to note that this reaction is still taking place, the forward and the reverse. Here's another way to look at it. Now this graph is showing rate of reaction over a period of time. So the forward rate, so this would be the hydrogen and iodine turning into, shifting to the right, turning into hydrogen iodide. It starts off really, really fast, and then the rate slows down. And then the reverse rate, of course, it's nothing at the beginning because we don't even have any products to turn back into reactants. So the reverse rate starts off very slow. It starts off at 0, and then it speeds up, and it speeds up, and it speeds up, and finally it reaches this point where now the two rates are equal. And we saw this in our sunbathers and swimmers analogy because for every one swimmer that became a sunbather, we had one sunbather that became a swimmer. These are equal rates. So that means the same amount is going back and forth. Now, chemical reactions aren't the only things that can have equilibriums, and you've probably seen examples, more examples of physical equilibria in your everyday life. Now let's take a look at water. So water at negative 50 degrees Celsius, so way below freezing, water at this cold of a temperature is going to turn into ice. And we would write the reaction or the process like this: water turns into ice. And we also know that at 50 degrees Celsius, if we have an ice cube at 50 degrees Celsius, which is pretty hot, this would be like the hottest day ever, it would melt and it would turn into water. So we would write the reverse of this taking place. But what happens at freezing point? Does water freeze or does ice melt? What happens? What really happens is both things at the exact same time at equal rates. So water is going to turn into ice at the same speed that ice will turn into water. So something's always happening. There's movement of water turning into ice and ice turning into water and freezing and melting. Something is happening. But to the person viewing, they're not seeing anything because they're seeing they're seeing the same amount of ice and the same amount of water. Nothing's happening to the naked eye. But what's really happening is ice is melting and water is freezing at equal rates. Now, where things get even more interesting is if we look at what would happen just below freezing point, so negative 1 degree Celsius. Now, you might think, okay, all water is going to turn into ice at negative, it's below freezing, but what really happens is we have a kind of equilibrium taking place. We have definitely a lot of water turning into ice, but some little ice particles, some frozen particles may melt, because some of those particles may be just going a little bit faster than your average freezing particles. So we would represent this with an arrow, a longer arrow pushing to the right and a shorter arrow pushing to the left. And we also see the same concept if we have water or if we have an ice cube at 1 degree Celsius. So that ice is going to melt. But there also might be a little bit of water maybe on the surface of that ice that freezes and turns back into ice. But for the most part, that ice will melt and turn into water. So we have an equilibrium arrow going to the left, a long one going to the left, and then a tiny little short one going to the right. Now these two scenarios don't worry about because they're a little advanced for this lesson, but just know that it is possible to have equilibriums that shift way to the right, but maybe just have a little bit to the left or go in reverse just a little bit and vice versa.